So in this particular unit, it's a relatively short unit. You're talking about exponential functions, about making graphs of exponential functions, how the different bases can affect the shape of the graph and whatnot. But for the honors component here, we're talking about solving exponential equations. So by that I mean something like 3 to the x equals 3 to the 7. This is actually an extremely simple one, and you might even be able to figure out a guess just by looking at it. But the question is, what do I raise the power, what power to what power do I raise 3 to get 3 to the 7? Now, we're not going to bother evaluating this because it's the exponents that I'm interested in. Really, in general, what we have is that if we have the same base, just like if you have an equation that has like x over 2 equals 3 over 2, we can multiply both sides by 2, or just kind of ignore them, and that gives us that x equals 3. It's the same idea here. If we have 3 to the power of x and 3 to the power of 7, that means x equals 7. Fairly straightforward. Another example similar to this is 3 to the x equals 27. Now here, these are not the same base. I mean, you can say that that's a power of 1, but that doesn't really matter. It's the bases that aren't the same. So the key thing for most of these types of situations is that we need to get the powers, we need to get the bases to be the same. So we need the same base. Need same bases. Call them like bases if you want, but that's the idea. So I need to rewrite 27 as a power of 3. Or I need to hopefully rewrite a power of 7 as a power of 3. So I can go down the list. 3 to the 1 is just 3. 3 squared is equal to 20, or is equal to 9, rather. 3 to the third, that equals 27. So this right here, this 27, I'm going to rewrite as 3 to the power of 3. And so that gives me that x equals 3. So that's how we would solve that particular equation. Next example. We have 3 to the x equals now 27 to the third. Now the 27 has a power, but that's okay, because we know, for example, again, that 27 is equal to 3 to the third, so I can rewrite the base of 27 as 3 to the third. Now I need to use my rules of exponents. My rules of exponents have that when I have a power inside a power like this, I multiply the exponents. So that gives me 3 to the 9. So now I have 3 to the power of x equals 3 to the power of 9, so x equals 9. That's how these work. We can make it a little bit more complicated, and I'll switch bases now. 2 to the x plus 3 equals 8 to the x. Again, we don't have the same base, so we need to figure out what base these both have in common and rewrite them as powers of the same base. So these are definitely important things for you to remember. 3 to the 2, 3 to the 3, and for that matter, 3 to the 4 equals 81. That's also a useful power for you to know. Powers of 2 are definitely useful as well. 2 to the 2 equals 4, 2 to the 3 equals 8, 2 to the 4 equals 16, 2 times 2 times 2 times 2, 2 to the 5 equals 32, 2 to the 6 equals 64. You could keep going forever, but realistically you're probably not going to see an example much beyond that. But that's the idea then. We have 8. 8 is a power of 2. It's the third power of 2. So I rewrite the 8 as 2 to the 3. 2 to the 3 to the x, again, we have a power inside a power. We multiply the powers. 2 to the power of 3x. So I have 2 to the power of x plus 3 equals 2 to the power of 3x. And now I do what I've done up here. I get that x plus 3 is equal to 3x. And now I have a little equation that I can solve. Subtract x from both sides. I get 3 equals 2x. Divide both sides by 2, and I get that x is equal to 3 halves. Which you could check by plugging it into your calculator. Plug into your calculator 2 to the 3 halves plus 3, so 1.5 plus 3, 2 to the 4.5. See if that's equal to 8 to the 1.5, and it should work out okay. And it doesn't matter if we have even more complicated examples. Ultimately, this process is going to work the same way. So, another example. 9 to the power of x equals 27 to the power of x plus 3. One strategy that you really need to be familiar with, these powers. The reason for this is it's very, very useful for you to be able to identify what powers you could use without needing to think about it a whole lot. So, for example, certainly 9 times 3 gives you 27, but we can't raise 9 to a power to get 27. But what I can do is realize that both 9 and 27 are powers of 3, so I can change them both. 3 squared to the x equals 3 to the cube to the x plus 3. Multiplying with exponents, I get 3 to the 2x equals 3 to the 3x plus 9. Make sure you distribute those. This then gives me that 2x is equal to 3x plus 9. Minus the 3x on both sides, I get negative x equals 9. And finally, x equals negative 9. X equaling negative 9 is my final answer there. If you do 9 to the power of negative 9, and then 27 to the power of negative 6, you can check that to see if it works out. One final example. Four to the power of x squared minus 1 equals 2 to the 3x. Right away, by this point, you should start to realize that 4, of course, is a power of 2. And so I can rewrite that as 2 squared. Distribute, I get 2 to the 2x squared minus 2 equals 2 to the 3x. And then from there, I get 2x squared minus 2 equals 3x. And this is the sort of problem that you've been solving for months now. 2x squared minus 2 equals 3x, it's a quadratic equation. 2x squared minus 3x minus 2 equals 0. Then you factor. 2x plus 1, x minus 2 equals 0. This gives us solutions of x equals negative 1/2 and x equals 2. So there's 2 solutions to this. And you can check them both to make sure that they both work. But there you go. Those are our solutions. Other powers that would be useful for you to know. 4 squared, of course, is 16. 4 to the third is 64. So sometimes you might be able to shortcut and use a power 4 instead of a power 2 if you have a 64. And one other useful thing for you to know, 5 squared is 25. 5 cubed is 125. And honestly, if you write out perfect cubes, because you know the perfect squares up to 100, or up to 12 roughly. If you write out and kind of familiarize yourself with perfect cubes too, then that would probably be useful as well. So that's it. Once you get to the point where you have these, once you get 2 bases that are the same, then you just get rid of the exponents. And then you solve from there.